Well, looks like we're live here. So it's Physics 1100 lab, and we're entering data. And so I remind you that you had your series of photo gates, you ran the sled, and you wrote down, here we go, you had your gate position, gate number, if you will. Excuse me, and there was a position, and let's see if we can make this a little bigger. And we're looking at level track. This is forward direction. For some, it could be left to right or right to left. It's basically the sled starts at gate 0 and goes all the way down the line to gate 5. And this is the easy one. And we have a time at each gate. By definition, we call the gate 0, 0. And then you see we have our delta S. And we have our time. Let me see. First of all, delta S is here. Here we go. So it's just, and there's a bunch of intervals. So the time at the end, the time at the, minus the time at the beginning. And so, in this case, not even spark timers or anything. It's straight, we know what the times are. We just wrote them down. Sorry, I'm doing 4 different labs this semester. And what is T average? We've discussed this before. If I'm going to make a plot like an XT graph, so that's this. Let's do a quickie here. And so we insert a graph. And so these are, let's see, we have to swap them just in case it might matter. Select data, switch row and column. No. We want to switch the axes. So this is kind of tedious, huh? Okay. That's, well, we'll call it gate position. It's not really correct, but. So now we have times. Hi there. And we have positions. So we have now a distance time graph. And it makes sense. So now it goes to 0. And if we want to get velocity, we're going to pick pairs of points. And we're going to get, if we do the delta S over delta T, that's the definition of average velocity. And so that basically is the value in the middle here. So we need the value of the middle in time. And the middle there it's the average time, just like we're creating an average. It's basically an average position divided by an average time. Well, let me think about that for a minute. Delta S over delta T, yeah, it's a triangular shape, so the midpoint is the average value of the time. So we just, here you go. So you add together T2 and T1, or T3 and T2, and then you sum them, divide by 2 in this case, but Excel has an average function. And that's just now, again, the center of each of those intervals here. Okay. And we have a delta S, just the difference between those two. And then a velocity is delta V over delta S. Delta X over delta T. All right. And we create our standard fit line. So we have a slope times the time plus a y-intercept. We've made our fit parameter table here. And then we have our residuals, data minus the fit, and our residuals squared. Now I have this standard deviation and error. That's for something else. I don't believe we'd be doing that with this lab. I forget why I put it there. Oh, when we were safe at home, we had time to compare how the fitting. I was demonstrating to the students that when you do a fit, when the line represents some kind of average value, uh, um, the fit line. What happens is that because we're looking at a changing. Well, the average value is the a. If I were to calculate the acceleration at every 2 points, in some sense that's the if I could then take an average value and a standard deviation of the sample, but we're not doing that. So I have my the sum of the residuals squared, and in this case, instead of typing this in by hand, so let's just say I'll make that. And that's interesting because it didn't look like the fit line changed. Oh, yes, it does. Right, and so maybe I could make that 50. Yeah, there. Now it moved, right? Okay, so just to let you see, we can let Excel do it. I think we've looked at this before. You have to install this solver. So you click Data, Solver, and there is the sum of the residual squared right there. I want to minimize it, and I want to vary the slope and the y-intercept. Make sure this is unchecked because you want to allow things to go negative. We solve, and there it is, minus. So what that means is, remember, since we're traveling in the positive direction, and we see a positive speed, a velocity, and the acceleration is negative, so the thing was slowing down. And so that means that you see it goes from approximately 45 centimeters per second and comes down to 42.25. So the magnitude is decreasing, it's slowing down. So you have then a velocity vector that's positive and an acceleration vector it's negative, and so it's all consistent. Now, one thing you can do is it's typical. We want to make the fit line a little bit longer and want it to go all the way to 0. And then we look at there, it looks like I'd like the fit line to go up to 3.5. And then I just take, I'm going to cut this and paste this. And I thought I did cut. Oh, anyways. So now I just drag this down and I get values. Oh, something's not right. Oh, okay. I see what I did wrong. I picked this t average are the x values for that plot. Paste it there. And that's interesting. What the heck is going on here? Oh, I know what. So I just got to redo this. And there it is. So now the fit line goes all the way through. And then this thing auto-scaled, so I'll just change the x-axis again. Now it goes all the way across. It's just a matter of taste. It looks nicer. And let's see what else we can do here. Well, that obviously can be jazzed up. Now, remember we talked about with the when you run it the other way, that we would get a graph that at the end of the day would pretty much look the same. And it's kind of rubs one the wrong way because we actually know we were going with a negative velocity. And I finally figured out how to deal with this, and thanks to one of our colleagues. So first what I do, I've taken my data, right? And you end up with, at the start point, indeed, that has the longest time because of the way the clocks were triggered and stopped, right? They get turned on one by one, and then when you get back down to gate 0, it turns them all off. So, of course, it gets you the longest time. But here's the key. What it can do then is, first of all, you see how I've listed them in reverse order because we started at gate 5 at 220, so I want that up top. These are the times I measured. And now look what I did, as this is the key contribution from our colleague, and that kept bugging me, was I find the delta t for each interval. And so you see how, just as before, now it's these two, etc., etc. Now that I have the delta t, and yeah, I see it's actually, you would have expected it would be the 2.04 first, but time can't be negative, so I arranged it so it's positive. So now I say, look, this is being that this is gate 5 here, 5, 4, so on. But anyways, I'm going to say that when I'm at gate 5, I want it to match up with the first measurement. So I know that I want that to be times 0. And then all I have to do then is I know that half a second passes, so I just add that half second, which is D31, to the time before. And in fact, once I do that, I can just drag this, because each time I'm taking the delta t and adding it to the previous time, and you see it accumulates. And in a sense, what I've done is I reversed these two. If you stare at it, it's not completely reversed. That's the subtlety. So you can't just simply resort these things. That's what made it so difficult. But we have the sense that at the beginning it's going faster, right? And it should be going slower and slower. And that's what we see. The delta t's are getting bigger and bigger. It's not very much because at the end of the day, and it doesn't look completely unequivocal. Well, you got to remember the acceleration is going to be quite small here. And we really haven't dealt with error bars. We're kind of sweeping that under the rug here. So that's one big leap. And I called it the scaled time. I don't know. One maybe could come up with a better amount than that. Now I go back up, and in fact, I have this table here, and I can just copy paste this table down to here. And look what I've done. I just said this equals that one here, B30. And now this equals the scaled times. So if I click on here, I would type in equals B30, whoops, then equals my first scaled time, and then I just use my fill handle, and there it is. Now, once again, the middle of each interval, there's a delta t that comes out of that. So that's the difference between those two. And then I need the center between those two. And once again, that's the average. So then this t average becomes my x values for the graph. And I have a delta t. And then notice that the delta s's become negative. Because, of course, I start at one gate, and when I move to the next gate, the position is a smaller number. And so, in fact, I get negative velocities, and then I've got my fit line going on, and we don't necessarily know that that's going to be a positive number or not, but when we graph it, we see that now it's great because at time 0, let's take a look. At time 0, well, in this case, it's time 0.5, and it was going from 220 to 190. My average velocity there was minus 60. And you see that it's slowing down. It may not be obvious, but it's slowing down because, and we remember though, it's obvious from our memory of the behavior of the sled on the air track because we had to shoot it up, and by the time it gets to the top, it basically stops and then, of course, turns around if we don't grab it. So we notice then that we get a positive slope down. Now, and once again, that's fine because it's slowing down, and that just says that the velocity and the acceleration are in opposite directions. And that's exactly right, because we get a positive acceleration, but our velocity vector is negative. It's pointing the other way. Now, the manual then says that we need to get the average value and the, in fact, what I just said a moment ago is wrong because this is a level track. So we actually didn't know that it would slow down when we went in the opposite direction. Excuse me. But the point is that we send it off in the negative direction from gate 5. We want, and we're not surprised that we end up with a negative velocity. Now, in this case, we really didn't know, as I contradict myself now, we didn't know ahead of time whether or not we would see positive or negative. So the contributors to this could be two things. Could be a tilt in the track, or it could be friction. Now, a tilt in the track will mean that the acceleration will always be the same sign. So and it's much easier to understand when it's actually tilted. We see that you started at some positive velocity and it increased because it was going down the track. That was our positive direction. And it picked up speed. So we have a positive acceleration, and we see the magnitude of the speed increasing. Down below, we're traveling at a negative velocity, but we're slowing down. And remember, now what I say is true. When I sent it up the track on this tilted track, we could obviously see that it was getting slower and slower. And so that's a positive acceleration. So both times we expect a positive acceleration. When we do the level track, we basically expect the two of them to both be zero. We expect it to the sled just to travel at a constant speed. But in this case, we see one is negative and one is positive. And the important point to note here is that in this case, as opposed to what we just looked at, in both cases, the speed, the magnitude of the velocity, the speed is getting smaller. And in that case, we conclude that it has to be friction. Because friction is a force and hence an acceleration that's always pointed in the opposite direction to the velocity vector. So just notice this guy is up to 21 minutes. And so, well, I'll stop this one and in a minute and go after I'll finish the level track. Then I'll go back to I'll start a new video for the tilted track. So in the manual it says that the average value is going to tell us the residual tilt. Oh, friction. The average of the two acceleration is the deceleration due to the friction, and the difference is the residual tilt. If there's no, it's not residual friction, it's whatever friction there is. I have to rewrite this. And tilt, residual tilt, yeah, we didn't get it quite level. So, let's take a look. If average, so what happens with average? We add the two of them together and we divide. So, right, if the two of them, let's think about that. So we're adding together, they could be positive or negative. And so if they're equal and opposite, then the average value would be 0 and there'd be no friction. And in this case, they're opposite, but they're a little bit different than each one. And I'm going to pause this for a minute.